This is going to be the first set of notes that we're going to have for atomic structure and periodic table. Before we get started into too much of the detail itself, we're going to be taking a look at some of the basic information that you should already have in your head, specifically protons, neutrons, electrons. You should already know the location of where these items are in the atom, at least in the general sense. We're going to get to more specifics on the electron. That's actually the purpose of this particular presentation. You should know the purpose of each of those subatomic particles, that the proton identifies which element that you're working with, and the neutron is going to stabilize the nucleus, and that the electrons are going to be what really affects chemical change. Charges, of course, for protons are +1, then electrons are -1, and then let's take a look at the mass here for a second. One of the things that you reviewed in nuclear chem is that the proton is actually weighs slightly less than that of a neutron, and that electrons, when it comes to mass, while it does have mass, it is substantially smaller than the protons or electrons. I'm sorry, protons or neutrons. Also, we've talked about the electromagnetic spectrum before, and that we have a full range of wavelengths, and that when you get into these higher frequencies, which are also going to be higher in energy or higher in electron volts, you're getting into the X-ray range and the ultraviolet range. As far as those X-rays and ultraviolets, some of those, actually the higher the energy goes, the more likely it's able to actually remove electrons off of atoms. So I wanted to make sure that you're aware that this is above the visible light range. We're looking at X-rays that are able to remove electrons off of atoms. So let's go ahead and get started. So imagine that you've got a soccer ball hanging from a rope, and you want to break the rope so the soccer ball can fly free. But you want to know what is the amount of energy needed to break the rope. So what have you got? You got a ping pong ball gun, you got a soccer ball attached to a rope. How do you figure out the amount of energy that you need to make the rope break? So if this is the information that you had, if you knew that the energy of the ping pong ball was 3,000 kilojoules, and you knew the energy of the soccer ball after it breaks loose still has 500 kilojoules of energy, how would you go about figuring out the amount of energy needed to break the rope? Okay. So the simple mathematics behind that is you would take the ping pong ball energy, subtract off the amount of energy that the soccer ball still has, and you end up with 2,500 kilojoules. So that's the amount of energy that was needed to actually break the rope. So now let's say that you've got a pool of soccer balls, all with different size cables, or at least with 3 different size cables, and you've got 3 energies of soccer balls coming out of this pool with a bunch of ping pong balls being shot in there. But remember that each ping pong ball is being shot in with 3,000 kilojoules of energy. If you got energy of soccer ball A at 50 kilojoules, and B is at 2,680 kilojoules, and energy of soccer ball C ends up being 2,970 kilojoules, how much energy did it take to actually break each one of those cords that were holding those soccer balls in place? We'll give you a moment. So the actual strength of the ropes, you'll notice that for A would have ended up being 2,950 kilojoules to break the rope. For B was 320 kilojoules to break the rope, and 30 kilojoules to break rope C. So you'll notice that the ropes themselves are of different strengths. Rope A ended up being the most tough or most difficult one to break free because it took that much more energy. And you'll even notice that it's almost like 10 times the amount. Like this is 320 is about 10 times greater than the 30 kilojoules. You'll even notice that this is almost 3,000. It's almost 10 times larger than the strength of rope B. So it gives you an idea of like the size or the strength of those ropes. So now we're getting back to the chemistry overall idea, and hopefully come back to this as well. So what we got then is the photoelectric effect. When high energy light hits a surface of a substance and electrons shoot off the surface. So just from the namesake, photo refers to light, electric is generally referring to the electrons, and the effect is the actual effect itself is the electrons flying off. So when high energy light hits the surface of a substance, electrons shoot off of the surface. Okay? So here's a general picture of it. You've got these red waves coming through here. They end up hitting these electrons. These electrons get some of that extra energy, and they start flying off the surface itself. So if we go back to the analogy of the ping pong balls and the soccer balls and so forth, the red waves coming in are the ping pong balls. The gray spheres shooting off end up being electrons, which are the soccer balls. And then the next question ends up being, well, what's the rope that's holding the electron actually in place? So it's the attraction that the protons in the nucleus have for those electrons. Okay, so, well, what factors affect how tightly these electrons are going to be held? Well, it's got to be something to do with the protons and the electrons themselves. So what are the options? Well, this is where Coulombs Law comes in. I know we've talked about Coulombs Law earlier in the year, but now it's time to take a look at this in more detail. You'll notice if I have a charge of substance A and charge of substance B, one at positive and one at a negative charge, and the distance between them is 1.5. If you want to say it's nanometers, that's perfectly fine. At the moment, we don't have to worry about the actual units themselves so much. But you'll notice that the force ends up being 1,000 for a baseline if there are 1.5 apart. If we end up doubling the distance between those same two charges, you'll notice that the force of attraction between those two charges ends up going down by a factor of 4. Okay? You'll also notice that if I quadruple the distance, so if we quadruple the distance here, from here, from here to here, this you'll notice is times 4. But you'll notice that we can go from here to here, it drops by a factor of 16. Okay? So you'll notice that as distance increases, the force dramatically drops down very, very quickly. If we were to make a graph of something like that, it would look very much like this, where this is the force and this is the distance. All right, so what about the magnitude? If we're talking about the magnitude of the charges, you'll notice that in each one of these cases, this time I have kept the distance between each of them the same, but I've changed the charge of the particle itself. By changing the charge of the particle itself, I want to take a look to see how the force changes. You'll notice that if I double the charge on the negative, the force of attraction is now also going to double. If I triple it, you'll notice that it triples the attraction. Same thing's going to happen, by the way, if we're comparing the charge from here to here. You'll notice that the positive charge got doubled, the negative charge stayed the same, distance stayed the same, and we still doubled the force. So there ends up being a linear relationship between the charge, the magnitude of the charge, and the force that is going to hold those particles closer to each other or attract them to each other. So in summary with that, Coulombs Law, biggest, strongest factor involved. Distance between the charges is based off the inverse square log. As distance goes up, the force of attraction between them is going to drop down by the inverse square. So it drops down very, very quickly. The magnitude of the charges is a second major factor. If you go from a +1 to a +2, there is going to be definitely a doubling of the force of attraction between the two. All right, so getting back to our figuring out the strength of the rope on the electron. What do we need to know if we want to figure out how much energy is holding that electron close to that atom? What do we have to know about that? Well, we need to know how much energy we're using to knock the electron off. We need to know the amount of energy that the electron has coming off of the surface when the actual electron gets kicked off. And once you subtract the two, we'll have the energy needed to remove that electron. And since we're doing it anyway, we might as well count how many of each electron we happen to be getting, so that way we actually have some type of total. So what does that all look like? Well, that's where we end up getting photoelectron spectroscopy. So PES, photoelectron spectroscopy. This is when you take a sample and you stick it inside of the machine and you hit it with high energy X-rays. The electrons that come off are measured, so we can figure out how fast they were going, how much energy they had. And we're going to count how many of each of those types of electrons are going to come off. Then you make a graph of it, and the graph is going to be number of electrons versus energy. So for example, here ends up being hydrogen. Hydrogen ends up having one peak. Okay? And you'll notice that we've got number of electrons on the y-axis, and on the x-axis, we have a funky kind of scale. Let's take a look very closely at this particular scale. And the College Board tends to use this type of scaling for this as well. This is a log-based scale. You'll notice I start off as 1,000, then the next one I end up having is 100. Then after that, I end up having 10, and then 1, and then 0.1. So you'll notice that these are each going up by a different order of magnitude. Okay? And you'll notice that the number of electrons that hydrogen has just is 1, which is why we just have the one peak. So you'll notice with helium, though, with helium I have one peak still as well, but the energy went up, or the size of the peak went up, because I have 2 electrons that are going to be doing that. So if I compare back and forth between these two, you'll notice that there's some other effect that's going on here as well. Hydrogen's is at 1.31, while helium's is at 2.37. So why the change? Why do you think there ends up being a change in that energy? If you end up saying that helium ends up having more protons than hydrogen, you'd be right. There's more protons in the nucleus, so we've ended up upping the charge that's on the inside of the nucleus, and that's going to hold those electrons in with more force, which requires more energy to actually get it to be removed. So what do you think is going to happen when we add lithium to the whole thing? So in other words, lithium is going to have an extra proton and yet another electron as well. But you'll notice that this time we don't get just a taller peak. We get 2 peaks. We have a peak that's at 6.26. We have a peak that is at 0.52. So why the difference this time? Well, for whatever reason, 2 of those electrons out of the 3 electrons that lithium has are at a higher energy than the other electron, the 3rd electron that's still remaining. Why would that be the case? Why aren't they all in the same energy? The reason for that is that the energy of the 2nd peak of this 0.52, this must have been electrons that were further away from the nucleus, which required less energy to remove it. So these 2 electrons required a whole mess of energy to remove compared to this 1 electron, which was substantially easier to remove. And again, take a look at the magnitude. This ends up being about 6. This is about 0.5. So these 2 are at almost 10 times greater, actually a little over 10 times greater, the amount of energy to remove them than this. Almost as if they're at an entire other level. Okay? So these are at one energy level, and this is at a different energy level. So we're actually going to call this energy level number 1, and this one we're going to call energy level number 2. So what do you think is going to happen as we go across the row of the periodic table? Well, we've got lithium, beryllium, boron, carbon, oxygen, nitrogen, fluorine, and neon. Are we just going to get that 2nd peak to get taller and taller? What's going to happen to the amount of energy? Let's think about that and let's take a look what's going to happen. So here's lithium once again, the same 2 peaks we had before. And now watch what happens when we go into beryllium. Flipping back and forth between lithium and beryllium, you'll notice that the height of this 1st peak stayed the same height. It didn't get any bigger, but this 2nd peak got larger. So an extra electron was added to that 2nd peak. You'll also notice that everything shifted to a higher energy. Everything shifted to the left, okay, for that energy. Boron. Wait a second. We'll take a look what happened there. So with lithium, we have 2 peaks. We have this first one, that really sharp peak that we have right here that we saw before. We have got another sharp peak. Now that these 2 sharp peaks are still there, but we said this one is at one energy level, this one's at a different energy level, and notice that there's still about 10 times difference between the 2 in energy. But now once we go to boron, we've got a 3rd peak going. So these two are really close in energy. This one is in a category by itself. So again, this one is in its own level. It's a sharp peak in its own level. And then these two over here end up having, they're in the same range of energy, but they're not all stacked up on top of each other. So these two have different energy. So it was actually easier to remove this electron than it was to remove these two electrons. And you'll notice when we go to carbon, that second peak raises up. Excuse me, I should say third peak. When we go to nitrogen, we get that peak to stand up even taller. Oxygen, fluorine, neon. So you'll notice that this sharp peak just kept getting higher and higher in energy. This sharp peak stayed at 2 electrons tall. And then this peak kept growing, growing, growing. Like that principal peak that principal peak was just getting taller and taller and taller. So if this is energy level 1, so if we're going to call that energy level 1, let me go ahead and get my tool. This is the first energy level, but there's a very distinct break between these two sides here. There is so much more energy in this side than there is on this side. And this is a sharp peak, so I'm going to call that first energy level. We call that 1s for the sharp peak, and there are 2 electrons in it. So this is we're going to call a 1s2 peak. This one is in the second energy level, and it's that first sharp peak that also only has 2 electrons in it. This last one is that principal peak because it's so much taller, and so this is still in the second energy level, the principal peak, and now I have 6 electrons in it. All right, so if I were to write an electron configuration for a neon, it would be 1s2, 2s2, 2p6. So while we're on that matter, let me go ahead and erase a portion of this here. We'll take this out for a second. Let's go back one and take a look at fluorine. So here's fluorine. It still has 2 electrons that are in that sharp peak in that first energy level. And we've got 2 electrons in a second sharp peak in the second energy level. And then we have that third peak, but you'll notice this time we only have 5 electrons in it. So this one, instead of being 2p6 like neon was, this is going to be 2p5. All right, so we're going to extend this same idea, and we're going to start taking a look at some of the other elements as well in the next row. But before we do that, let's take a look to see once again what happened to those peaks over time across the periodic table. So moving back to lithium. Lithium had 2 electrons in that first 1s energy level, and this one has 1 electron in the 1s energy level. So lithium would be 1s2, 2s1. Beryllium, 1s2, 2s2, but you'll notice that all those peaks, again, shifted to a higher energy. This is now going to be 1s2, 2s2, 2p1. Carbon now ends up being 2p, so 1s2, 2s2, 2p2, 1s2, 2p2, I'm sorry, 2s2, 2p3 for nitrogen. Oxygen, again, 1s2, 2s2, 2p4. Got back to fluorine, which we've done already. And neon is now going to be 1s2, 2s2, 2p6. Take a look at sodium. Go ahead and take a moment to try and figure out what the electron configuration for sodium is going to be based on the photoelectron spectroscopy data. So you'll notice that there's this still big separation. Now it takes 104 megajoules per mole of energy to actually knock the electrons off of this first energy level over here. And then we have this energy level, but now you'll notice we got down to 0.5 again. So these two are almost 10 times greater in energy than this one happens to be. So what we really now have is a new energy level. So if we're looking at that new energy level, we now have 1s2, 2s2, 2p6, 3s1, because we only have one electron in that, which then brings us to magnesium. So you'll notice that fundamentally speaking, all three of these peaks are still at the same type of three peaks that sodium had, except again, they're shifting. Once again, why are they constantly shifting to a higher energy? Well, magnesium has one more proton in the nucleus than sodium did. And then you'll notice that this energy over here, now I've got 2 electrons in it, and the peak ended up getting higher. Aluminum, you'll notice that that then split again. So magnesium, aluminum, magnesium, aluminum. The aluminum has this extra peak that the magnesium did not. And then silicon, the rays is going to constantly keep going higher and higher. And so we're going to have that same pattern. 1s2, 2s2, 2p6. Now we're at a 10 times lower energy. So this is 3s2, 3p6. What do you think potassium is going to look like? Take a moment. So potassium started a new energy level again. So you'll notice that we have that same type of breakdown that we had before. And let's actually write this one out so you can get the whole thing. 1s2, 2s2. This peak is 2p6. This one is 3s2, 3p6. And now this is the 4th energy level. That's now going to be 4s1. Once again, you'll notice it's just 1 because it's only one. The peak is only 1 electron tall compared to the other ones that are there. Calcium compared to potassium does the same thing once again. You'll notice that all of the peaks once again still shift to a higher energy, and we now have 2 electrons in that last energy cloud of 4s2. All right, so let's talk about some conceptual questions. Why is the energy difference between levels almost a 1 order of magnitude, or a power of 10? And the atoms in a row get smaller in size as we go to the right. In other words, if we're looking at lithium and then beryllium, boron, carbon going across the periodic table, those atoms, even though we're constantly adding more electrons to it, those atoms are getting smaller and smaller and smaller as we go across the periodic table. Why would that be? So to answer those questions, the energy difference between the energy difference being a magnitude of 10 is because those electrons must be further away from the nucleus. So that attraction is using that inverse squared law of Coulombs law, holding those electrons tighter in, which requires more energy to remove them. As we're going across the periodic table, the reason that the atoms are actually getting smaller in size, though, is because we're constantly adding more protons. So we're increasing the positive charge inside the nucleus, which is that second idea that we're talking about from Coulombs law, pulling those electrons closer in and getting them smaller as we go across. So what should you have gotten out of all of this? The more energy, the closer the electron is to the nucleus. From the left to the right in a period on the periodic table, so going across a row, since there are more protons, there's going to be higher energy, smaller atom. The outside electrons get pushed out slightly due to the core repulsion. We didn't talk about that one much. I will do so in the future. Next thing to also watch out for is the College Board with that graph will sometimes have the numbers going from a low value to a high, or from a high value to a low. In this particular presentation, I was using all values that started high and went low. Sometimes the College Board reverses it. They have kept pretty consistent with this, but just I want to make sure that you are still checking out the axes that are in the axes and the units that are in the graph that you were given. You should also be able to label from highest energy to lowest energy, starting with 1s. So the 1s is that first energy level with a sharp peak and it has 2 electrons in it, and continue from there. So this is where we're starting off with atomic structure. We are adding the photoelectron spectroscopy, which you probably haven't seen before. We will have more notes on this sometime in the future.